Steve Mould's video was basically about. In the video, they basically argued and proved that pulleys work. They conserve momentum and they violate kinetic energy. So the simple truth is you can put a force here in this direction and you'll get twice the energy, okay, in the sense of you can have the lighter object. So I can make this a 10 and this a 5. All right. And the 5 mass will move. For any movement in the 10 mass, I'll get twice the motion in the 5 mass, and vice versa. So I can move the 5 mass up and down, and I can make the 10 mass move 1/2 the velocity up and down, or vice versa, indicating it's completely momentum driven. There's no evidence that kinetic energy can be reasonably applied because, frankly, I put a force in this way and I get twice the energy out this way, or I put a force in over here and I get half the kinetic energy out on the other side. It makes no sense. So somebody draw me an example of pulleys not conserving momentum completely, reliably, dependably, and always. Show me where kinetic energy works in here somewhere, because it doesn't.
Here's the weighing of the masses that we'll be using for this demonstration. So we've got 174 grams, that'll be his 2 mass, and that's his 1 mass, which is 87.53, so it's a little bit over by half a gram. Yeah, 87.53, and that's just 2 mass. Oh, let's get that more central. 174.03. Yeah, so the half mass is just a touch over. Yeah, but close enough. No need for words and pictures when you can do a physical demonstration. So this is just a simple pulley system with a mechanical advantage of 2. The weights are on, unfortunately, way too much friction in the system, so I'll have to do it by hand. I was hoping I could just drop it and show it, but for the purposes of the demonstration, it'll still show the point. So on this rod, the entire length of the rod is 54 centimetres. There's a marking there at 27, which is half of the rod, and the 2 mass should be dropping, but I'm going to have to pull it down. So that will be going half the distance of the rod. Now on the other side, it would have to reach the top of the rod in the same amount of time, because obviously as this moves in the same amount of time, it'll move a distance. If it moved to the top of the rod, it'd move twice the distance in the same amount of time, therefore it would gain twice the velocity. I've got to employ the use of the head cam for this one because I need both hands, so it's really difficult through the camera. So like I say, we'll have to imagine that these were dropping. So that's roughly at half the distance of the rod. And if it was to fall, boom, 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 the other side goes up. And eventually we see that it's around about half the distance. So that fell twice the distance of this one went up. So if we were to consider momentum, obviously, if this was to fall, boom, and this one goes up, this went twice the distance and it's a 2 mass, this went half the distance and it's a 1 mass. So momentum is not conserved in pulley systems. Like I say, ideally, you know, if it hadn't got so much friction, I could just drop it and boom. But as you can see, it only reaches half the distance, not twice the distance, half the distance. Twice the distance would be to the top there, because it's falling from half the distance of the rod here, so twice the distance would be the top. And obviously inversely, if it's to pull this down the 13.5 centimeters, this one goes up to a distance of half the rod again. So what would I say, 13.5, 27. So it's a complete inverse of what you're claiming. So momentum is not conserved in pulley systems, which is quite clear, but energy is. From the demo, we can see we had the two mass moving, just call that one distance in 1 unit of time, and the one mass moved half that distance in 1 unit of time. So the one mass is going half the velocity. So if we look at that in terms of momentum, we've got, just say, two mass going 2 velocity and one mass going 1 velocity. So we'd have a momentum of 4 and a momentum of 1. So clearly momentum in pulley systems is not conserved. If we just take a look at this in terms of energy, that's the pulley system. So we've got a mechanical advantage of 2. Just say the weight here was 100 newtons. Obviously we've got 2 ropes pulling it up, so we've got 50 newtons here and 50 newtons here, which would equal the 100. But we've got a weight of 100 newtons. So the whole point of this system is to make it easier, because we've got 100 newtons of force, but when you pull on the rope, you only have to pull with a force of 50 newtons, so it makes lifting something that's heavy, you know, you apply less force, but obviously you've got to do it over twice the distance, because obviously when you pull this rope's moving up and this rope's moving up, so twice the distance on the pulley here, when you pull it down, will only go up 1 unit of distance here. So the force would be 50 newtons over twice the distance to lift this 100 newton weight force up 1 distance, or 1 displacement. Obviously work is force times distance, so the weight itself that's being lifted is a weight force of 100 newtons, and it would displace 1 distance. So energy wise, that would be 100. On the where you're pulling it, obviously you've got the reduced force, but you're pulling it for twice the distance, so you've got 50 newtons of force over twice the distance, and that equals 100. So the energy is conserved.